Hey, Math 30-2. So we're continue on here. We're doing probabilities using counting methods. So remember that a couple chapters ago, we used counting methods such as permutations and combinations to make committees, to order people around, to make passwords. We use also the fundamental counting principle to do so as well. So we're going to use those in conjunction with probability, sample spaces, and calculate the probability of such events happening. Now, what remember from those previous chapters is when do we use, or what do we use permutations and combinations for? So when order is important, so order matters here, we're going to use permutations. Okay. And when order is not important, order is not important, we're going to use combinations. So using the C notation, NPR, using combination NCR, we should be able to determine at least how many of the favorable outcomes happen, and then we can also use these to determine how many total outcomes, sample space, there is, and then we can take those two numbers and we divide them, and we can get our probabilities. All right. So let's say in this first one here, we want to create a committee of 5 people, selected from 10 females and 8 males. So what I know is that is 18 total people to choose from in our committee. And our committee doesn't mention anything about positions like treasurer, president, vice president, and stuff. So I'm going to assume that this order does not matter. So we're going to be using a combination here. Okay? Order does not matter. Sorry about that. So what's the probability that there'll be exactly 3 females on the committee? So remember last time, a couple of chapters ago, to figure that out, we're going to use our combination. So we're going to write down how many committees that we can create using exactly 3 females. We're creating a committee of 5 people. So that means I'm going to take, of the 10 females, I want to choose 3 of them. I don't care about order, so that's why we're using combinations. And of the 8 males, I need to choose 2 more because it's exactly 3 females. So I have 3 females, 2 males. So I can create, based on my numbers here, I can type these in my calculator. Let me just type them in. So I get 120 times 28, and I get 3,060 different ways, different committees I can create using exactly 3 females. Now the probability of this happening, so the probability, let's call this event A. This is my event. The event is exactly 3 females on the committee. So that's event A there. Okay. So to get that probabilities, I have the total number of favorable outcomes, which is this top number, this 3,360, and I want to divide it by the total in the sample space. So how many in total are there, the total in the sample space? Well, what I know is that there's 18 people and I need to choose 5 of them. That's just all the different committees you can create, right? So that there is 8,568 different committees. Now, if I punch this in my calculator and reduce this down, that becomes 20 over 51, and I get 0.392 for that one. Okay? So it's about 39% chance that of the committee that they create, if it's just randomly selected, there's going to be exactly three females in that committee. Here's the next one. Let's just call this event B here. So event B being exactly 3 males on the committee. So we go through the same logic that we had before. I want to know how many are in my event and how many in the sample space. So my event has to have exactly 3 men. So I'm going to have 8 choose 3, and then I'm going to, out of the 10 females, finish up my committee, 2 more there. Then I already knew this number. This is the total number of committees of my 5 here. So this is going to be 8,568 still. Top number is slightly different. My top number is going to be 2,520, just 20, sorry. So you just punch these both in your calculator, get that top number, reduce this down. So 5 over 17. Now, if I were to look at these fractions, I wouldn't know which is which, like which is the more favorable one. But according to this, just randomly selecting males and females and exactly 3 of them is about a 29% chance that that'll happen. So it's more favorable to have more, exactly 3 females. Now, for my next one, event C, let's call this one event C. Okay, I want exactly 2 females in the committee. Now, I'm going to start writing this out. So, number of favorable ones. And while I'm thinking about this, while I'm writing this out, I'm going to realize that, 10 choose 2. That's for the females. I have 8 men. I want to choose 3. That's exactly the same as the one above it. 18 choose 5 on the bottom. That's exactly the same. So this will be also 5 over 17. Because if I chose exactly 3 men, it means I have exactly 2 females as well. There we go. Okay, so let's look at the next one here. So we have 3 people lining up. Okay, so we're lining up here. So that means this is going to be a permutation question because order matters here. We're lining up. Order matters. And you can see in the question here, in descending order or ascending order. So descending order means, if you don't recognize that word, descending order means if you talk about age here, like 18, 16, 14, and those are the ages of the people, that's descending. The number is going down. Ascending means they're going to go the other way. 14, 16, 18, the numbers are going up. So that's ascending order, right? So what's the probability that they line up in descending order? So let's call this event A. Okay, let's call this event A up here. So event A, what's the number that will happen? Assuming that they're all different ages like this. So let's say I had 18, 16, and 14. What's the probability they can line up in descending order of age? Well, there's only one way to do that. Well, that's a pretty easy one. And then what are all the ways I can rearrange these people? Well, I have 3 people, and I want to pick them because the order matters, so 3p3. Or I could just think of this as fundamental counting principle, where I have 3 people in line. I have 3 choices for the first person, 2 for the next one, 1 for that one, which turns out to be 3 factorial, which ends up being 1 over 6. Any one of these works for all this one. Now, for the other one here, for event B here in ascending order, the number of times that we get in ascending order over times all the ways I could rearrange those 3 people. Well, that's 6 again on the bottom because it's the exact same as the one above it. And then there's only one way to do that. So it's 1/6, just the same as above. All right. Now, Gwen, Morgan, Arthur, and Kay volunteer among 5 other students. So this is key here, is other students. So these 4 and these 5 add up to a total, which might be useful, total of 9 students. Okay, they're volunteering to go on the school math team. It doesn't look like there's any key positions here, so order doesn't matter. So I'm just going to put that in here. Order does not matter. Okay. All students have equal ability. Okay, so one's not going to be chosen over another one. That just kind of makes it fair. Determine the probability that all 4 of these people will be chosen to be on this team of 5 spots. So we have 5 spots here. So my event is having all 4 of them will be chosen on this team. So let's call that event A. So event A would be the number of times that those 4 people will be on the team over the total number of teams possible. Okay, so the total number of teams possible is pretty easy. We have 9 students and you need to choose 5 of them. So there's 126 different teams. Okay, now the number of teams would be, I have these 4 kids that I need to choose. So there's only one way to do that. And then I have 1 more position to fill. So I have 5, choose 1. So that ends up being exactly 5. So it's not a very likely thing if some person just randomly picked these kids. It's going to be like a 4% chance. in order to do percentages, you just times by 100, move the decimal place 2 times. So it's not a very likely situation. They just chose them all at random. 4% of the time, these 4 kids will be on the same team. Okay? Let's do another one down here. So let's just, because that one's up there, so this one's A, let's call this one B. So in this one here, we're playing a game of Crazy Eights. They dealt 8 cards from a standard deck. Determine the probability that the hand will consist of exactly 7 hearts. 7 hearts. Okay. So I want to know how many times does that actually happen, and how many possible hands are there. So the possible hands, again, that's pretty easy. There's 52 cards. I want to choose 8 of them. So there are a lot of possible hands here. 7, 5, 2, 5, 3, 8, 1, 5, 0. So 752 million possible hands out there. Yeah, it's quite a bit of hands, right? Now, the other one's a little bit trickier. We want exactly 7 hearts. So there's 52 cards in a deck. If I divide them by the 4 suits, that means there's 13 hearts. There's 13 of each of them. 13 clubs, 13 spades, 13 diamonds, and 13 hearts. Okay, so I have 13 hearts, and I want to choose 7 of them. Okay, and then I have one more card. So if I want exactly 7 hearts, I don't want a heart again, so I can't choose from another heart. So that means I only have 39 cards to choose from, and I want to choose one more. So what we got here is we got 17, 16 for the first one. We get 39 for the next number there. And we get 6, 6, 9, 2, 4 for that top number. Let me just write this bottom number out again. There's a 3 in there, sorry. And what we're going to do is just going to reduce this down as much as possible. You can punch in your calculator. Not a very nice number. It's times 10 to the negative something. So we can leave it here. I want to reduce this down as much as possible, though. So it ends up being this. Now, not many calculators can actually create this fraction. I just said, okay, well, let's just divide the top and bottom by 2 and see what happens. Looks pretty good. And then I thought some other numbers you could try to divide by. Can't divide by 2 again. Can't divide by 5. It looks like this as far as this one goes. So there's my probability. Okay. Not very likely. Not very likely will happen at all, but that's fine. Let's keep it going. Okay, so Nigel spells out the word cookbook using Scrabble letters or something. So he has all these letters with them, or a bunch of blocks with letters on them. Turns them face down, mixes them up, then asks Kendra to arrange the tiles in a row and then just turn them face up. Okay, so he jumbles them all up, and then Kendra goes along and just flips them all. If they spell the word cookbook after that, Kendra wins the book of recipes. Okay? What's the probability that this will actually happen? So what's the probability that Kendra will win? Right? So what are the number of times that you'll have a winning combination here? And how many ways can I rearrange all the letters in this little deck here? Okay. So there's only one way to win. You spell cookbook. That's it. It looks like the word cookbook, and that's the only way you can actually win this, right? You flip them over, it says cookbook, and you win. Any other way, you don't win. Now, there are different O's here and stuff, but if you see the word cookbook, you've won. That's the only way you can win. Okay? There's only one way. So there's only one way to spell cookbook. So you have the one way. Now, the bottom here is a little bit trickier. So we have 8 letters. And I have to remember that when we did these rearranging letters, one, we had to deal with the repetition of letters. We had to get rid of those. Well, let's just say these are all unique to start off with. So there are 1, 2, 3, 4, 5, 6, 7, 8. Now, if they were all unique, there would be 8 factorial ways of rearranging. Like I would have 8 letters. I have 8 choices for that one. 7, 6, 5, 4, 3, 2, 1. Now multiply them all together. And that's how many ways you can rearrange the letters in the letter cookbook. But you have to remember that some of these O's and some of the K's there, if I just flip the K's, it's still the same word. If I flip the O's, they're the same word. So I have to get rid of that repetition. So to get rid of the repetition, you have to count how many times they repeat. So O repeats. If I look at this, my O's repeat 4 times. So I'm going to say 4 factorial. Then my K's repeat 2 times. So I'm going to say 2 factorial. So there's 24 ways to rearrange those O's. There's only 2 ways to rearrange the K's. So I need to get rid of that. So you punch all in your calculator. At the bottom, you get 840. So there's a 1 in 840 chance that this Kendra will win the cookbook in this case. Okay. To access a particular online game, password that's password protected, every player must create a password that consists of 3 capital letters, okay, and followed by 2 digits. Following these conditions, determine the probability the password chosen will contain an A, B, and C if repetition is not allowed. Okay, so first of all, I want to know how many passwords there are. So A, B, or C in this one. Repetition is not allowed. So I want to know how many passwords are in this total sample space. So well, there's kind of a really big line here, so maybe I'll just erase that. And then I also want to how many different ones will have A, B, C's in them. So the total number of passwords that I'll have will be 3 capital letters, 1, 2, 3. Repetition is not allowed. So that means I have 26 choices for the first letter, 25 for the next one, 24 for the next one. Then I have followed by 2 digits, 10, 9. Okay, so that's all on the bottom there. I can multiply that all out and get a really big number. What does it end up being? 1,404,000. But I'm not too worried about that right now because I'm going to just simplify this down beforehand so I get a better fraction. Okay, now the next part here, how many of these actually contain A, B, and C? So if it contains an A, B, and C, that means you only have 3 letters. It doesn't specify they have to be in that order. So if A, B, and C, I have 3 choices for this one, 2 and 1. Those are my letters. And then I don't really care too much about these ones. 9 and 10 again. Okay. Now I'm going to make my fraction here. So what I'm going to do is I'm going to just simplify this down. Everything here on the top is multiplied with everything on the bottom. So these are all kind of factors. So remember rational expressions, we could just reduce factors out. So I can reduce those 2 out. This ends up being a 6. And there's a 24 here on the bottom. So maybe I can divide those 2 as well. But right now what we have is 6 over, and I just pull out my calculator, 26 times 25 times 24, 15,060. And I was like, okay, maybe I could just divide them both by 6, and I get 1 in 2,600 passwords will have an A, B, and C in it. Okay. What if repetition is allowed? Okay. So same setup. How many of those passwords have A, B, C's? How many passwords are there? This is an S, not a 5, sorry. Well, if repetition is allowed, that means I have 26 times 26 times 26 times 10 times 10. So that's all my passwords on the bottom. That's a lot. That's pretty big. It ends up being 1.7 million this time. Okay. On the top, we have A, B, and C again. So A, B, C. So we had to have those 3 letters. Then times 10 times 10. So I just follow the same logic we did before. 10s, I can cross those off. I have 6 here. Now maybe I can reduce that down. I don't know. But right now I have 6 over 17,776. Technically I can reduce that one more time. So just divide both top and bottom by 2. And this is what we get. So 3 out of 8,788 passwords will have ABCs in them if you were allowed to repeat letters as well. There you go. So in this case, we're using a fundamental counting principle to do this one. Okay, we have 2 more questions here. Pretty simple, then we'll finish up this video and this lesson, and then we'll continue on the next video. Okay, so high school athletics team is forming a beginnings curling team to play in a social tournament. For the 4 positions, skip, third, and second in the lead, there were 12 students, including 4 more, including these 4 friends. So in total, there are 16 students here. Okay? That's nice to know. So you're just going to add the 12 plus the 4. That might be useful for later. What do we have here? What are the probability? Well, we also have some key. Every student has an equal chance of being chosen. Okay, what's the probability that 4 friends will be chosen for this team? Okay, so what's the probability of all 4 friends to be on this team? Well, how many different teams can I make out of these 4 friends? So you want to know how many teams can I make using all 4. I'm going to divide it by all of them, so my total sample space here. So if I have 4 friends on this team, and order matters because I have a skip, a third, a second, and a lead, I could have 4P4, so order matters here. So I have 4 kids, I want to pick all 4. Now how many teams can I actually make? Well, I have 16, and I want to pick 4 of them for this teams. So that's what that looks like. So on the top here, I have 24. On the bottom here, I have 43,680. So you just punch them in your calculator. So I get 1/1,820. So remember, you can find these P buttons and these C buttons in your math onto the calculator. So in your calculator, hit the math button here. All right, my calculator looks backwards. Hit the math button. Go over to probability. I don't know if you can see that here. It's kind of backwards here, but P and C are the second and third choice there. Okay, so it's a 1 in 1,820 chance that all 4 friends will be chosen at random to be on the same team. Now, what would the probability be if there were 14 instead of 12 there? It seems like a pretty simple question. It's the very same kind of question. There's still 24 teams that the 4 friends can make, but now it's going to be 4. Yeah, so if I put this here, there's going to be 18. Oops. It's going to be 18 students in total because you got the 14 plus the 4. Okay. So that means there are 18 P. Why did I put a C there? I said I was going to say P. Okay, 18 P4. And we get 73,440. So a 1 in 3,060 chance of being on the same team. Considerably less when you just add a little bit more students to it. There you go. Oh, I want to express this as a percentage as well. So this percentage, it says it here, express your answer as a percentage to the nearest hundredth. So as a decimal, this number is as a decimal, this number is quite small. 1/1,820. Then I'm going to times it by 100. So to change this, you're going to times whatever you get here by 100%. Change it into a percentage. And when you do that, you get 0.05 hundredth, that's it, 5%. So hundredth is 2 decimal places. You can do the same thing with this one. You can times it by 100%, and you get 0.03%. Okay? So not very likely that all 4 kids will be on the same team. All right, so that concludes this lesson. We'll continue on to the next lesson. We'll probably split this next one into 2 pieces here for you. And yeah, I'll see you in the next lesson. Continue doing those practice worksheets, and I'll see you then. Bye.